Hello students. So welcome back students. In today's class that I am going to discuss micro instructions. So this concept is also very important here. So in previous classes as I have discussed about hardwired control and micro program control in detail, right? So today let us see about micro instructions, right? As you know, having described a scheme for sequencing micro instructions, we now take a closer look at the format of individual micro instructions. Right here, a straightforward way to structure the micro instruction is to assign one bit position to each control signal, as it was shown in the previous discussion. That is, assigning one bit position to each control signal. Right. However, this scheme has one serious drawback or a disadvantage that we can say, that is assigning the individual bits to each control signal that will result in a long micro instruction because the number of required signals is usually large. Moreover, only a few bits that are set to 1 in any given micro instruction, which means that the available bit space is poorly used. Now again consider the simple processor and assume that it contains only four general purpose registers, that is R0, R1, R2 and R3, and some of the connections in this processor are permanently enabled, such as output of the IR to the decoding circuit and both the inputs to ALU, they are enabled. Assume that they are enabled. The remaining connections to various registers that require total of 20 gating signals or 20 gate signals. Now additional control signals are now shown as that are needed, including read, write, select and WMFS and end signals. Finally, we must specify the function to be performed by ALU, that is arithmetic and logical unit. Now let us assume that there are 16 functions that are provided, including add, subtract, and XOR operations. So these functions depend on the particular ALU used and do not necessarily have one-to-one correspondence with the machine instruction opcodes. So in total it is 42 control signals that are needed. By adding all this, so we can say that total 42 control signals are needed. So if we use simple encoding scheme, then 42 bits would be needed in each micro instruction. So fortunately the length of the micro instructions can be reduced easily. So most signals that are not needed simultaneously and many signals are mutually exclusive. For example, only one function of ALU can be activated at a time. Here, the source for data transfer must be unique because it is not possible to get the contents of two different registers onto the bus at the same time. So, read and write signals to the memory that cannot be active simultaneously, that we know already, right? So, this will suggest that the signals can be grouped so that all mutually exclusive signals are placed in the same group, and hence at most one micro operation per group is specified in any micro instruction. Then it is possible to use a binary coding scheme to represent the signals within a group. Now consider, for example, 4 bits are sufficient to represent the 16 available functions in the ALU. So register output control signals can be placed in a group which is consisting of PC out, MDR out, Z out, offset out, R0 out, R1 out, R2 out, R3 out and temp out. So any one of these can be selected by a unique 4-bit code. Now Further, the natural groupings can be made for the remaining signals, as you can see in this particular figure. So this figure shows an example of a partial format for the micro instructions in which each group occupies a field which is larger enough to contain the required codes. So most fields must include one inactive code for the case in which no action is required. For example, all zero pattern in F1, so that indicate that, so you can see here F1 is there, right? So all zero pattern in F1 indicate that none of the registers that may be specified in this field should have its content placed on the bus, and an inactive code is not needed in all the fields. For example, F4 contains 4 bits that specify one of the 16 operations performed in ALU. Since there is no spare code is included, and hence the ALU is active during the execution of every micro instruction. However, its activity is monitored by the rest of the machine through the register Z, which is loaded only when Z-in signal is activated. Now, grouping the control signals into the fields that requires a little more hardware, because decoding circuit must be used to decode the bit patterns of each field into the individual control signals. The cost of this additional hardware is more than offset by the reduced number of bits in each micro instruction, which will result in a smaller control store. So as shown in the figure, only 20 bits are needed to store the pattern for 42 signals. As you can observe this thing in this figure. Kindly analyze this figure. So this figure shows that only 20 bits are needed to store the patterns for 42 signals. So is it clear? Can you agree with this point? So you just add these bits from F1 to F8. So only 20 bits are needed here to store the patterns for 42 signals, right? So far we have considered grouping and encoding only the mutually exclusive control signals. Now we can extend this idea by enumerating the patterns of required signals in all the possible micro instructions. Here each meaningful combination of active control signals that can then be assigned a distinct code that represent the micro instructions. So such full coding is likely to further reduce the length of micro words, but also to increase the complexity of the required decoder circuit. Here, highly encoded schemes that use the compact codes to specify only a small number of control functions in each micro instructions that are referred to as vertical organization. That is very important. On the other hand, the minimally encoded scheme in which many resources can be controlled with a single micro instruction, that is called as horizontal organization. So these two terms are very important here, vertical and horizontal organization. I'll repeat. Highly encoded schemes that use the compact codes to specify only a small number of control functions in each micro instruction is referred as vertical organization. On the other hand, the minimally encoded scheme in which many resources can be controlled with a single micro instruction, that is known as horizontal organization. Right? So the horizontal approach is useful when a higher operating speed is desired and when the machine structure allows the parallel use of resources. The vertical approach results in considerably slower operating speed because the more micro instructions are needed to perform the desired control function here. Although few bits are required for each micro instruction, and this does not imply that the total number of bits in the control store is smaller. So the significant factor is that less hardware is needed to handle the execution of micro instructions. Here, horizontal and vertical organizations represent the two organizational extremes in the microprogrammed control. So many intermediate schemes that are also possible here, in which the degree of encoding is a design parameter. The layout, as it was shown in the previous figure, means this figure. So this layout is a horizontal organization because it groups only mutually exclusive micro operations in the same field. As a result, it does not limit in any way the processor's ability to perform various micro operations in parallel. Although we have considered Although we have considered only a subset of all possible control signals, so this subset is representative of the actual requirements. Here we have omitted some details that are not essential for understanding the principles of operation. So next I will discuss about the microprogram sequencing. As you know, the simple microprogram example in the previous figures that require only a straightforward sequential execution of micro instructions, except for the branch at the end of fetch phase, instruction fetch, right? So if each machine instruction is implemented by a micro routine of this kind, then the microcontroller structure, as it was suggested in the previous figure, in which micro PC, that is micro program counter governs the sequencing, would be sufficient. So a micro routine is entered by decoding the machine instruction into starting address that is loaded into micro PC, that is micro program counter. So some branching capability within the microprogram can be introduced through special branch micro instructions that specify the branch address, which is similar to the way branching is done in the machine level instruction. So with this approach, writing the microprograms is fairly simple because standard software techniques can be used here. However, this advantage is encountered by two major disadvantages. That is, having a separate micro routine for each micro, that is for each machine instruction, result in a large total number of micro instructions and a large control store. If most machine instructions involve several addressing modes, then there can be many instructions and addressing mode combinations. Here a separate micro routine for each of these combinations would produce considerable duplication of common parts. So we want to organize the micro program so that the micro routines share many common parts as possible. So this require many branch micro instructions to transfer the control among the various parts. Hence, a second disadvantage is that execution time is longer, means execution time is more because it take more time to carry out the required branches. Now consider a more complicated example of a complete machine instruction, that is the instruction of type add a source comma or dest. So which will add the source operand to the contents of register R dest and places the sum in R DST, that is the destination register, right? Now let us assume that the source operand can be specified in the following addressing modes, that is a register, auto increment, auto decrement and indexed, as well as the indirect forms of these four addressing modes. Now we use this instruction in conjunction with the processor structure to demonstrate a possible microprogram implementation. So a suitable microprogram is presented in the flowchart form. As you can see this flowchart form. This is for the easier understanding, right? So the entire micro program is presented in this flowchart form. This is for understanding purpose. Here, each box in the chart correspond to a micro instruction that control the transfers and operations indicate within that box. The micro instruction is located at the address indicated by the octal number above the upper right hand corner of the box, and each octal digit represents 3 bits. We use the octal notation in this example as a convenient shorthand notation for the binary numbers. So most of the flowchart in this figure is self-explanatory, but some details need to be elaborated here. So first I will explain the issues involved, then examine the flow of micro instructions in this figure, that is in detail. So first one, take the branch address modification using bit o-ring. So this is important. Branch address modification using bit o-ring. Here the micro program as it is shown in this particular figure shows that the branches are not always made to a single branch address, that we can observe here, right? That is, the branches are not always made to a single branch address. So this is a direct sequence of combining simple micro routines by sharing the common parts. Now consider the point which is labeled with alpha in this particular figure. So at this point it is necessary to choose between the actions required by the direct and indirect addressing modes. If the indirect mode is specified in the instruction, then the micro instruction in the location 170, that is this micro instruction which is at the location 170, that is performed to fetch the operand from the memory. So if the direct mode is specified, so this fetch must be bypassed by the branching immediately to the location 171. So here you can see branching. The most efficient way to bypass the micro instruction 170 is to have the preceding branch micro instruction specify the address 170, then use OR gate to change the least significant bit of this address to 1 if the direct addressing mode is involved. So this is known as bit O-ring technique. Bit O-ring technique for modifying the branch addresses. So this technique is very important here. An alternative to the bit O-ring approach is to use two conditional branch micro instructions at the location 123 and 143 and 166. Another possibility is to include two next address fields within a branch micro instruction, one for direct and other for indirect addressing modes, and both of these alternatives are inferior to the bit O-ring technique. The next one is wide branch addressing. So as you can see in this particular figure, so this figure includes a wide branch in the micro instruction at the location 003. The instruction decoder, which is abbreviated as inst dec, that is inst dec, that is instruction decoder. So it generates the starting address of the micro routine that implements the instruction that has just been loaded into the IR. In our example, register IR contains add instruction, for which the instruction decoder generates the micro instruction address 101. However, this address cannot be loaded as it is into the microprogram counter. The source operand of add instruction can be specified in any of the several addressing modes. Here the figure shows that 5 possible branches that the add instruction may follow. From left to right, these are indexed: auto decrement, auto increment, register, direct and register indirect addressing modes. Here, the bit orring technique described above it can be used at this point to modify the starting address which is generated by the instruction decoder to reach the appropriate path. For the addresses as it is shown in the figure, the bit orring should change the address 101 to one of the five possible addresses values, that is 161, 141, 121, 101 and or 111 depending on the addressing mode that is used in the instruction. So this is about wide branch addressing. Next is WMFC, that is use of WMFC. Here we have assumed that it is possible to issue a wait for MFC command in the branch micro instruction. So this is done in the micro instruction at the location 112. For example, which causes a branch to the micro instruction in the location 171. So combining these two operations introduces a suitable problem. The WMFC signal means that the micro instruction may take several clock cycles to complete. If the branch is allowed to happen in the first clock cycle, then the micro instruction at the location 171 would be fetched and executed immediately. So to avoid this problem, the branch must not take place until the memory transfer in progress is completed. That is, the WMFC signal must inhibit the WMFC signal must inhibit any change in the contents of the microprogram counter during the waiting period. So this is all about WMFC. Now the detailed explanation or detailed examination of this. Now let us examine one path of the flowchart as shown in this figure, that is in more detail, right? So let us examine one path, right? Now consider the case in which the source operand is accessed in the auto increment mode. So this is the part which is needed to execute the instruction, that is add r source plus r dest. Now consider this instruction, add r source plus r dest, where R source and R dest are the general purpose register which is shown in this figure. So this figure shows the complete micro routine for fetching and executing this instruction, that is executing add R source plus R dest. We assume that the instruction has a 3-bit field used to specify the addressing mode for the source operand as shown in the figure. So bit patterns 11, 10, 01 and 00 that are located in the bits 10 and 9, which will denote the indexed auto increment, auto decrement and register modes. Means the bit patterns 11, 10, 01 and 00, so they will denote indexed auto decrement, auto increment and register modes respectively. Now for each of these modes, bit 8 is used to specify the indirect version. For example, 010 in the mode feeds specify the direct version of auto increment mode, whereas 011 specify the indirect version. We also assume that the processor has 16 registers that can be used for addressing purpose and each is specified using a 4-bit code. Thus, the control operand is fully specified using the mode feed and the register indicated by bits 7 to 4. The destination operand is in the register which is specified by bit 3 to bit 0. Since any of the 16 general purpose register may be involved in determining the source and destination operand locations, right? I'll repeat. Since any of the 16 general purpose register may be involved in determining the source and destination operand locations, Here the micro instructions refer to respective control signals as R source out, R source in, R dash out and R dash in. So these signals must be translated into specific register transfer signals by decoding the circuitry which is connected to R source and R dash address fields of the IR, that is instruction register. So this means that there are two stages of decoding. First one is micro instruction feed must be decoded to determine that an R source or R dash register is involved. Here the decoded output is then used to get the contents of R source or R dash feed in the IR into a second decoder, so which produces the gating signals of the actual registers R0 to R15. Here the microprogram that has been derived by combining the micro instructions of all the possible values in the mode field, which will result in a structure that requires many branch points. So the example as shown in this figure has a two branch points. So the two branch micro instructions are required. So this is all about the micro instruction for add, that is R source plus R dest. So I'll continue with next class. Thank you.